Hi, everybody. Today I'd like to do a short video that explains omitted variable bias, or OVB as we call it. And we'll explain it by starting with the case of a single variable regression, where our model is that earnings depends on education. And there are other factors encapsulated in the error term, other factors that uh, explain part of the variation in earnings. And so this is our model for every observation, for every I, for every possible observation in our population. We would say that earnings depends on education and other factors. So that's our model. We go to get a sample of data from the population and we estimate this equation, this single variable equation, and we estimate beta 1 hat, the slope parameter, and beta 0 hat, the intercept. Now, this slope parameter, beta 1 hat, that we estimate will be unbiased if this assumption holds. This assumption is that the expected value of the error term, remember our error term is all the other factors, so the expected value of the error term conditional on the level of education is equal to 0. That assumption that the expected value of the error term conditional on education equals 0, meaning the errors on average. Remember, the expectation operator is the probability weighted average. So the errors on average are equal to 0. They're just as likely to be high as to be low, just as likely to be positive as to be negative, so that they add up on average, probability weighted to be equal to 0. That's the same thing as saying there are no confounders, no other factors that are correlated with education and also causing earnings. So our definition of a confounder is some other variable that's correlated with education and also explains earnings. If there were confounders, if our assumption that there's no confounders were not true, that is, if there were another factor correlated with education and causing earnings, then beta 1 hat would not be unbiased. Beta 1 hat would be unbiased. We would have omitted variable bias. The expected value of the coefficient would not be equal to the true coefficient, and we'd have a biased coefficient on average. Remember that our estimated coefficient is a random variable itself because we could take many samples and have many different beta 1 hats that we calculate. So saying that beta 1 hat is biased means on average, the expected value of beta 1 hat is not equal to the true beta 1. So we imagine there's some true beta 1. So let's take a little bit closer look at this. Omitted variable bias can arise when we have a candidate omitted variable. We'll call it Z. So whenever we can imagine or think about an omitted variable that meets a two-part test, so that has to satisfy two conditions, two assumptions about this Z as something we think about based on our contextual knowledge of the situation. In this case, the specific situation is how education affects earnings. And this two-part test is that this Z variable has to be correlated with X, so it can't be a zero correlation. The correlation between X and Z is not equal to 0, so it could be either a positive correlation or a negative correlation. So that's condition 1. And second part of the two-part test is that Z independently causes Y. So Z has some effect on the outcome. So two-part test. Every time we're talking about omitted variable bias and proposing a specific variable to, I think this variable is the omitted variable, we have to ask, does it satisfy this two-part test? If it doesn't satisfy one of these two conditions, then there's no omitted variable bias. So if the Z variable is uncorrelated with X so that the correlation is equal to 0, then there's no omitted variable bias. If the Z variable does not independently cause Y, in this case earnings, then there's no omitted variable bias. Once we think of a Z, and there could be more than one omitted variables in any equation. We could have, 5, we could have a dozen, we could have just one, or we could not think of any omitted variables. Once we think of a omitted variable, we can ask how is the beta 1 hat biased? In what direction? Positive, negative, larger, smaller? It'll be complex to think about the direction, and we'll have to be very careful in our wording because there are going to be 8 cases, and we're going to have to work through each of these cases. And these cases, when we work through them, will be especially tricky when the underlying coefficient, the true coefficient, is negative, because then when we want to talk about the direction of the bias, uh, when we have negative numbers, it's not always clear what the direction is. Say we think our true coefficient is -4 and our bias coefficient is -8. So is -8 bigger than -4? Well, it's bigger in absolute value, but it's smaller on the number line, right? -8 is a smaller number than -4. So it'll be very confusing when we talk about things like that. So we always want to be really careful with our wording, and the chapter guides you through exactly how to word this. Um, let's continue on and work through one particular case here. So we'll imagine that there's an omitted variable in our education and earnings case, and that omitted variable is ability, or that confounder, 2 words meaning the same thing. The omitted variable or the confounder is ability. So ability and education attainment are probably positively correlated, right? People who are more able to do logic and reasoning and writing and mathematics probably stay in school longer. People who aren't good at that, who don't have that ability, they don't have a hard time finishing high school. They might drop out of high school as soon as they turn 16. They stop. Maybe they go into vocational school. They pursue some other career. This general ability that we're thinking about, we don't know how to measure it. We're just imagining we can measure it. We can imagine there's some IQ test or some general ability test that people take when they're kids, and that's the kind of ability that we're talking about before, different from education, different from what you learn in education. And presumably most of us would think, yeah, more able people are probably likely to stay in school longer because schooling definitely rewards that general ability, and it's always nice for humans to be rewarded, to get gold stars and things like that, to get A's, right? So people who are generally able tend to continue in education, so the correlation is positive. It's also pretty reasonable to think that this ability underlying attribute of people is probably positively affecting earnings. When you start working, your bosses recognize you as being pretty able and having high ability, and so you get promoted and you get a raise. They want to retain you, right? So there's a 2-part test, and this variable, this confounder, satisfies the 2-part test. The correlation between ability and education is likely to be positive, and ability likely affects earnings. So we can then conclude that beta 1 hat would be biased. And now we want to see what's the direction of the bias. To understand the direction of the bias, we'll go through 3 steps. We'll imagine the true relationship. We'll imagine how the errors in our single variable regression, remember, earnings equals beta 0 plus beta 1 times education plus the error term. So we'll imagine how these errors are distributed, positive or negative, relative to the true relationship. And then we'll see what the estimated line will look like if we had a sample of data. So let's go. It's pretty straightforward in this case. We have earnings, we have education, and we imagine a true positive relationship here. Then we say, what's the likely, sorry, I jumped to. We go, what's the likely distribution of errors? Well, if people who have high education, these are high levels of education, if people who have high education also have high ability, then their earnings are likely to be higher than warranted by their level of education because they also have high ability. So the errors are likely to be positive for high education people. For low education people, on the other hand, the errors are likely to be negative because low education people are also disproportionately low ability people. So their errors are likely to be negative. The other factors that are determining their earnings are such that their earnings are even lower than they would be based on their level of education, because that other factor is ability, and that other factor is reducing their earnings. Whereas people with high education, the other factor, which is ability, is increasing their earnings. So we have a pattern then of errors or of observations that looks like this. When we go to fit our estimated line through this pattern, the red line will be our estimated slope using the sample observations, and we'll try and fit right the best line through the scatter plot. I've drawn the scatter plot in obvious, pretty exaggerated way. So the best line fit is going to be steeper than the true, what we imagine to be the true line. So that helps us understand that in the single variable case, beta 1 hat, which is this slope, so that's beta 1 hat. Let me make this so it's not vanishing. Where is this? Here we go. So beta 1 hat, which is the red line, is going to be greater than beta 1 true. So in the positive case, it's pretty straightforward because we know what greater than and less than mean. In the negative case, it's not always clear what we mean by that. But in this case, it's pretty straightforward that our slope will overestimate the true relationship between education and earnings. And I like to use this language when we talk about this, and I encourage you to use the same language. When we look at this graph, we say, how to understand our biased coefficient. We'll say it looks like education affects earnings a lot. It looks like education affects earnings a lot, but that's wrong because people with high education also have high ability, and people with low education have low ability. So education doesn't actually matter as much as we thought it did. Our estimated coefficient is biased. It's in this case, too large. It makes it look like education matters a lot for earnings. Sure, education matters, but not as much. The true slope is flatter than our estimated slope. Our estimated slope is biased. So that's how we work through the direction of the bias in this first very simple case. And you want to practice this case a lot and then start moving on to the other cases, and I'll make videos with the other cases.